Oh, oh dear. Now you got to hear me clicking. I hate that when I make you hear me clicking. All right. How's it going? And I also thought I'd put a freaking discussion board on Blackboard. Everything takes me 4 times to do. I don't here sometimes, but it's like, I put a discussion on my 210 without any trouble. I go to try and do 220, and it's a freaking nightmare. But anyway, so my frustrations with technology continue. Sometimes I kind of miss the good old days of living. First of all, you lived in total ignorance of what the students were thinking. Because they couldn't email you or call or anything like that. And you just came and well, this was also high school, so it was a little bit different. Um, it's funny because when I first started teaching, it was we didn't even have computers at our desk. When I started in 1997 or 98, we had that. Anyway, it's just come a long way. So, but that's still not an excuse for doing a crappy job of explaining voltage and the differences between. So I'm going to do homework problems 31 because they're kind of important. It's kind of important to know, and I also like the way this book does things. And I didn't want to do them because I was going to go, oh dear, I should have probably looked at these before I started. So now I've looked at them, so we're ready to go. So this put them all on this one thing. I think it'll only take about 8 or this whole thing will be about disregarding my rant on trying to get a discussion board. Okay, so we've got two equal potential surfaces surround a 2.8 times 10 to the negative 8 point charge. How far is the 280 volt surface from the 60 volt surface, potential surface? So let's take a look at the picture. All right, so let's not take a look at the picture. Let's take a look one more time at the 2.8 times 10 to the negative 8. Okay, so that's good. So here we go. We've got, so on problem 31, we've got this Q is equal to positive 2.8 times 10 to the negative 8 coulombs. And he's so tedious. I know I am. I am sorry. And V1 is equal to 280 volts, and V2 is equal to 60 volts. Okay, so now we've got those on there. Now, I've got a question for you. Which one of these, I've got this positive 2.8 times 10 to the negative 8 coulomb sitting here, all right? Which one of these guys is closer? Which one? It's a positive, so as we get closer to positive charges, the potential goes up, right? So the 280 is closer. So here's the 280 volt, and then the 60 volt is out here somewhere. 60 volt is out here, all right? Now, if I release this proton, if I release this positive charge, it's not a proton, if I release this positive charge, it's going to want to go this way. It's going to go from a higher potential to a lower potential. It's going to gain kinetic energy and lose its potential energy. But we need to know the distance between here, this delta S, right here. Okay? Well, that's pretty easy to do because I've got this formula, and I didn't do a good job. The voltage of a point charge, this is a point charge, the distance away, R, is equal to KQ over R. So V1 is equal to KQ over R1. Well, so you've got 280 is equal to 9 e to the 9 times positive 2.8 e to the negative 8 divided by R1. Well, you can solve for R1, right? Cool beans. And then R2, V2 is equal to KQ over R2. And here's R2. And then your overall, so you do the same thing. Now, solve for R1. I'm not going to do that for you. Solve for R2. And then R2 minus R1 is what they're after, is equal to your change in S. Okay? And we can also probably compute the electric field Well, I know we could compute the electric field for a point charge because the electric. Now look at this. This is why that electric field times the charge, or times the distance is equal to the potential. Because to find, now this is a bonus for the exam, because to find the electric field at the point P here at P1, which is a distance R1 away, the electric field at P1 is equal to, E is equal to KQ over R1 squared. Okay. Now, notice what happens when I multiply by R1. Aha! I get KQ over R1. See how that works? All right, let's do the second problem. There's a little hint on that one. Now let's look at 32. And this time I promise I'll write down all this stuff. Oh, this one's so much fun. It says an equal potential surface that surrounds a point charge Q. All right, so I don't know Q, and I'll show you my scribblings here in a minute. The surface area, the area is 1.95 meters squared. Equal surrounds a point charge. Okay, so we're assuming a sphere, and the V away again. The voltage, the point we're looking at is 456 volts. So let's take a look at what this is saying. Here's what we've got. I've got this positive charge Q here, okay, and then I've got this equal potential surface. It's around here, and somewhere on this surface, R, that's R2, this is also R, okay, is my charge. Let's put it on this one right here, okay. This whole thing, this whole sphere around it is a potential of 456 volts. All right, I got a question for you though, real quick, before we move on. Let's say we put a little charge out here. Let's say we put an electron here. Now this is unrelated, just keep it in mind. How much energy does it take to move that electron from here to here along this surface? Right. Change the energy required is equal to 0. Requires no energy. Staying on the same plane. All right, but you guys are going, yeah, whatever. How the hell did we solve this? All right. Well, we do the same thing. We get VQ. V is equal to KQ over R. But what the heck is R? Ah, they told us kind of right here, because this is the surface area of a sphere. And the surface area of a sphere is the area is equal to 4 pi r squared. Aha! Now we're on to them. So I know that 4 pi r squared is equal to 1.95 meters squared. There you go. And then solve for Q. So you take this, stick it in there. This is given. This is given. This you solve for Q. And knock yourselves out. Okay, and I've also found that big E for using exponents on Wiley plus big E or little e works. It's flexible that way. All right, out here